So good morning, Year 11, and today we're going to go through the idea of dynamic equilibrium, which again is all about preparing you for chemistry paper 2. This is for foundation tier and higher tier. So we're going to go through the first sort of key concepts that cover both foundation and higher, which is the idea of what a reversible reaction is, the energy changes that are involved in reversible reactions, and this idea of equilibrium. Then we're going to move on to the higher tier concepts and how different factors can affect the equilibrium. So we're going to look at concentration, temperature, and pressure. So if you're foundation tier, you're only going to watch up to where we get up to equilibrium, and I will say on the video when to stop. Again, this is not a normal lesson by any stretch of the imagination. This is about going through the key concepts ready for paper 2. So we're going to start first of all with reversible reactions. Just to remind you, these booklets are also with the video, so I would advise printing them off and annotating them as you go through. And if you have any questions, don't hesitate to send me an email or ask me in lessons as and when we see each other during the exams. So I'm going to start with what the idea of a reversible reaction is. So can you see how I've got A plus B, which would be what we call our reactants. And if it's a reversible reaction for foundation tier as well as higher tier, you do need to know what that symbol means. So that symbol there means reversible. Okay, and you need to be able to identify that. So in other words, what we're saying here is A reacts with B to make C and D, which we would call our products. But in a reversible reaction, what we're also saying is actually our products, C and D, could react together to actually make A and B. So it's the idea of reactants making products, and our products can then go back to make our reactants. And we need to really understand what's going on in terms of the amount of reactants, the amount of products, and when we then reach something called an equilibrium, which is what we're about to go on to now. So I'm hoping you can see I've got a lovely graph here, and I want to first of all just underline this key point here. Equilibrium can only be reached if we are in a closed system. In other words, things cannot enter the reaction and things cannot leave the reaction. And that's the conditions that's required for equilibrium to take place. And you'll sometimes see that on the exam question. It will say in a closed system. And that's a hint for you that it's got to do with equilibrium. So you can see I've got my graph here. And the graph is showing the rate of the reaction and the time that it takes. And if you look first of all at this line here, we can see that this is the forward rate of reaction. So when we're looking at our reactants up here, this is for A plus B gives me C plus D. So I'm going to write that up here. So A plus B gives me C plus D. That is the rate of the forward reaction. So during the chemical reaction, you can see that the amount of our reactants is actually decreasing. So we're going to annotate that. So this is going to be showing that as the reactants react, so as they react together, the concentration of these will begin to fall. Okay, so A plus B starts to go down. And that then means that our overall rate of reaction will decrease. And that's because we've got less amounts of A plus B, because they're reacting together to make C plus D. Okay, so that's why that line there shows clearly that the amount of A and B is decreasing, and therefore the rate will decrease. Okay, so that's why that line's going down. On the other hand, as A and B begin to decrease, well, that means we're making more of our product. So this here will be our product, the reverse rate of reaction. So as you can see, we're making more C and D. So the C and D levels are starting to go up. So let's say that. So more product is formed. So the concentration increases. So their concentration will increase. And if their concentration increases, that means the rate of reaction will increase. You can read my scruffy handwriting, guys. Will increase. So that's why we can see that the reverse reaction begins to increase, because as these react together, their levels will start to drop and begin to form more product. And as more product gets formed, those products are going to react to make these products here. So eventually what we reach is something called equilibrium. And as you can see, this here is where we've got the rate of the forward will be going at the same rate as the backward reaction. And that's essentially what equilibrium is. So let's write that down. So the rate of the forward reaction, okay, so the rate of the forward reaction will be going at the same rate as the backward reaction. Okay, and that's because as A and B fall, we make more C and D, and as we make more C and D, then actually their numbers will begin to fall and make more A and B. So eventually we reach what we call an equilibrium, where the forward rate of reaction is the same as that of the backward rate of reaction. So at equilibrium, both reactions are still happening, but there's no overall effect, and we call that a dynamic equilibrium. So I just want to make sure we understand what a dynamic equilibrium is. So can we just put a little heading, dynamic equilibrium? Okay, so essentially, when we reach this forward and backward rate of reaction being at the same rate, both reactions are still happening, but there's no overall shift. So there's no overall shift towards the products or shift towards the reactants. They are in the rate of reaction is the same. Okay, so let's write that down. So at a dynamic equilibrium, both reactions are still happening. Okay, so what I mean by that is A plus B is still giving me C and D, and C plus D is still giving me A and B. So both those reactions are still occurring, but there is no overall effect. So in other words, I'm not shifting it to one side. And this is where closed systems are so important. Because if this wasn't a closed system, we might, for example, make a gas here, and that gas could escape. So therefore, that would affect the equilibrium. Okay, and that's where it's important to understand that when you have reached equilibrium, and in the case of a dynamic equilibrium, the system needs to be closed because both reactions will still be happening, but there's no overall effect, there's no overall change in the system, if you think of it like that, but no overall effect. Now, there's a couple of things that will affect so a couple of things that affect dynamic equilibrium. So they are concentration. Okay, so the concentration of reactants and products. Okay, so that can affect the dynamic equilibrium. And we need to ensure that it's a closed system. So we don't want to lose any products, and we don't want to add anything extra into the reaction. So a closed system is where none of the reactants or products can escape. Okay, so they can't escape and nothing can enter. So in order to ensure we reach a dynamic equilibrium, we need to have what's called a no overall effect on the reaction. Okay, so the forward reaction is going at the same rate as the backward reaction. And to do that, we need the concentration of the reactants and products to not change, because that would affect it. And we need a closed system so that we're not losing any products and nothing can enter to affect the reaction. And that's essentially what a dynamic equilibrium is. Now, for higher tier, we then talk a little bit about where the equilibrium shifts to. And that's usually because we've changed something. Okay, so for foundation tier, we just need to know that the dynamic equilibrium is where both reactions are still happening, but they're happening at the same rate. And that's what's going on here with this line. You can see that that is what is occurring. And in order for a dynamic equilibrium to be reached, we require the system to be closed and that the concentrations of reactants and products do not change. Okay, so hopefully that explains what equilibrium's all about. So I'm going to talk to you a little bit about the position of the equilibrium. So again, this is coming under this heading here. So again, this is still foundation tier. So we're still going to go through this, and I will, like I said, highlight when we will shift over to the higher tier concepts. So here's a typical reversible reaction. I know it's a reversible reaction because of the arrows. And I've got ammonium chloride breaking down using heat. So we call that thermal decomposition to make ammonia and hydrogen chloride. And if I cool that, that will then reverse back to form ammonium chloride. And this is where potentially an equilibrium could in fact form. So if I look at conditions that would favour the forward reaction and conditions that would favour the backward reaction, that's when I have to look at what information is above each of the arrows. So for example, if I apply heat in this case, I will favour the forward reaction. So heat will allow me to go from this side of the reaction to this side of the reaction. So by heating up the ammonium chloride, I am going to shift the equilibrium to the right. Okay, in other words, I'm going to make more product, and eventually I'm going to make less ammonium chloride. Well, ammonium chloride levels would go down. Okay, if I want to go from here to here, so from the right to the left, well, actually, I've got to take away that heat energy, so I've got to cool it down. And that will then favour the backward reaction. So you've got to be aware that the position of the equilibrium can be changed depending on the conditions. So if I have heat applied to the system, I am going to favour the reaction to the right. If I cool the reaction down, I'm going to favour the reaction to the left. So you can see that I've changed the position of the equilibrium either to the right or to the left, depending on the temperature. So when a reaction is at equilibrium, it doesn't mean the amount of reactants and products are equal, okay? It just means that the rates of reaction are either in balance, okay, if it's a dynamic equilibrium, or they are favouring one reaction over the other. So heat, for example, will favour the production of ammonia and hydrogen chloride, whereas cooling the solution will favour the equilibrium to the reverse reaction to make more ammonium chloride. So the conditions can dictate which way we are shifting our equilibrium, which is why this is about the position of the equilibrium. So let's just write some things down about that. So when our reaction is at equilibrium, we're not saying that we have the same amount of reactants to products. So it doesn't mean the amounts of reactants and products are the same. And that's important to point this out, okay? Because depending on the conditions, I am going to shift my equilibrium either to the right or to the left. So if the equilibrium lies to the right, okay, so heat's been applied in order to shift and break down the ammonium chloride to form these two products here. Then what I'm saying essentially is the concentration of the products is greater than that of the reactants. Okay, so the concentration of the products would be greater than the reactants. Now, if it was the other way around and the equilibrium lay to the left, then what I'm saying there is that the concentration of the reactants would be greater than that of the products. So again, we're going to write that down. So if the equilibrium lies to the left, then that means that the concentration of the reactants would be greater than that of the products. Right, and that is what it's all about. So you have to be able to spot, depending on the conditions that's required. So again, that's hinted at in the equation. I heat the solution, heat the ammonium chloride, and break the compound down via thermal decomposition, and that's going to favour the equilibrium to the right. So therefore I make more products than my reactants. However, if I cool it, then my equilibrium shifts to the left, and I make more of the reactants than I do of the products. So that's important. Now, the overall position of the equilibrium depends on 3 factors. So we're going to write those 3 factors down. And those 3 factors are temperature, they are concentration of reactants and products, and they are also pressure. So these 3 factors can and will shift the equilibrium either to the left or the right, depending on the reaction. And that starts to push into the higher tier concepts there. So just be mindful for foundation tier, you just need to be aware that these factors can affect the equilibrium. But for higher tier, you need to explain each of these in turn and how they would affect the equilibrium. So last thing from a sort of a foundation point of view is this idea of reversible reactions and exo and endothermic. So you'll already know what these 2 words mean from paper 1. So endothermic means that energy is taken in from the surroundings, and exothermic means that energy is given out to the surroundings. So knowing that, I would therefore know that if I apply heat to the hydrated copper sulfate, that's going to favour the forward reaction. So it's going to shift from the left to the right. And if the reaction is reversible, then the conditions would be the opposite to the forward reaction. So if the forward reaction is endothermic, then that means the backward reaction would be exothermic. So in this case, I would want to cool that reaction down, and that would shift it to the left. Sometimes you might get a reaction where the forward reaction is exothermic and you have to work out what the backward reaction would be. So it's important to know that if the forward is exo, then the backward would be the opposite, which would be endo. So it's just knowing that they're going to be the opposite to each other. So we're going to write that down. So in a reversible reaction, in reversible reactions, the reaction can be endothermic in one direction, then it will be exothermic in the other. So it's just the opposite to each other. So in a reversible reaction, if the forward reaction is endothermic, then the backward reaction would be exothermic. Okay, so that's where we're going to stop now. So with your foundation tier, that's all that you need to be aware of in terms of reversible reactions and equilibrium. But if you're foundation tier, so now's the time to stop the video. If you're higher tier, we're going to continue on to look at the other factors that can affect this rate of reaction. So the equilibrium, So we talked about temperature, pressure, and concentration. So we're going to look at each of those in turn. So like I said, foundation tier people, you're all good to go now. We're now going to move on to look at the higher tier concepts, which as you can see are highlighted here. And we're going to begin by looking at temperature. So you will have been taught this through this concept of Le Chatelier's principle, which again, I'm going to write down what that principle actually means, and understanding what that principle means can then help you to explain why, if I increase the temperature, what will happen to the equilibrium? If I decrease the temperature, what will happen to the equilibrium? Because this principle basically underpins each of these scenarios. So I've decided to choose the Haber process reaction, because again, that comes up in paper 2, and it is a green topic, so it does hint to me that that potentially could be linked together. So I wanted to give you a reaction that you're familiar with. And we're going to look at each of these factors in turn. So as I said, there's 3. So we're going to start with temperature. So I want to start first of all, though, with telling you what this concept actually means. So what does that, the principle, what it actually is it? So essentially what it is if you change the conditions, because remember, in a dynamic equilibrium, the conditions don't change, okay? So, but if I change the conditions of a reversible reaction when it is at equilibrium, then the system counteracts that change. Okay, so the system will try to counteract that. So the system will counteract that change. And you are expected to then be able to predict the effect of that change. And when we look at temperature, pressure, and concentration, we're going to be referring back to this concept. So if you change the conditions in a reversible reaction at equilibrium, the whole system will try to counteract that change. And I'll look at temperature with you first of all to try and explain what we mean by that. So we're talking about the Haber process here. Okay, so as you'll remember, the Haber process is the production of ammonia. We have nitrogen reacting with hydrogen to make ammonia, and ammonia can break down again to make hydrogen and nitrogen. So I'm going to write out this equation again. So I've got nitrogen plus hydrogen goes to give me 2 moles of ammonia. And you need to be aware, and you should be aware from the other video, that the forward reaction is an exothermic reaction. And the backward reaction is therefore going to be endothermic because it's always the opposite. And we know that from the sheet earlier on. So if Le Chatelier's principle is correct, okay, if I change the conditions at equilibrium, so for example, if I decrease the temperature, then the system is going to try to counteract that. So by decreasing the temperature, I will in fact favour the forward reaction. So I would have a shift in the equilibrium to the right. So decreasing the temperature will favour the forward reaction and shift the equilibrium to the right. And that makes sense because it is an exothermic reaction for the forward reaction. So decreasing the temperature would favour the exothermic reaction, shifting the equilibrium to the right. So again, have I changed the condition of the reversible reaction? Yes, because I've decreased the temperature. As such, I'm going to shift the equilibrium to the right because the system will try to counteract that change. And it would be the opposite if I increase the temperature. So increase in temperature is going to therefore favour the backward reaction. Okay, so it's going to favour the backward reaction. And therefore, it is going to shift the equilibrium to the left. Oops, and shift. So in other words, I'll make more reactants. Now you'll remember that in the Haber process, the temperature they decide upon is around 450 degrees Celsius, which isn't ideal for the forward reaction because actually we want it to be really cold. But that's not what we're covering here. That's covered in the Haber process video. But essentially what we're saying is, if you decrease the temperature and the forward reaction is exothermic, that's going to favour the forward reaction and therefore shift the equilibrium to the right. If we decrease the temperature, because obviously these will be opposite, then that's going to shift the equilibrium to the left. So essentially we're changing the conditions, and as a result, the system tries to counteract that change and will therefore shift it one way or the other. Okay, and you are expected to predict that. So we should know that an exothermic reaction gives out energy to the surroundings. So if we cool the surroundings, that means more energy can be transferred quicker. So therefore, it would favour that reaction. Okay, so that's why we can predict that it would move to the right. If we know already that endothermic reactions take in energy from the surroundings, well, if we heat the surroundings, that means energy can transfer quicker. So therefore, we would shift the equilibrium to the left. So that's essentially what we're asked to do. So that's what temperature does to the equilibrium. And it's all about whether the forward and the backward reaction is exo or endothermic. So just be mindful, look at the equation they give you, look at the information above the arrows. That is always an indication to help you to work out which way the reaction will go. The next thing we're going to look at is pressure. So again, I'm keeping the equation the same, just because I do think it will link to the Haber process. And we're going to annotate this equation because we should know already that nitrogen would be a gas, hydrogen is a gas, and ammonia is a gas. Okay, so pressure really only affects the equilibrium if it involves gases. So we're going to write that down. So changing the pressure only affects the equilibrium if it involves gases. So only affects an equilibrium involving gases. And that's why I've picked this reaction. Okay, so pressure's to do with gases in this case. Now, obviously, we have to work out from this which direction, depending on increasing or decreasing the pressure, we would expect the equilibrium to shift. Now, that depends on the number of moles of gas. Okay, so that's going to be really important here. So if I look on the left-hand side of the reaction, I have got in total 4 moles of gas. I've got 3 moles of hydrogen and 1 mole of nitrogen. And over here, I have got 2 moles of ammonia. And that's going to be important later on, but I just want to be mindful that you have to look at really the number of moles on each side, because that's going to be basically pressure will affect that and try to shift that. So if I increase the pressure, as you know, Le Chatelier's principle, the equilibrium will try to counteract that. So if I increase the pressure, the equilibrium tries to counteract it. So in other words, it's going to try to reduce the pressure. So in this case, because I have 4 moles of gas here and 2 moles of gas there, there's less molecules on this side because there's only 2 moles of ammonia. Okay, so that would shift the equilibrium to where there's fewer molecules of gas. Okay, and that's where Le Chatelier's principle comes in. If I'm increasing the pressure, the system's trying to counteract by shifting it to wherever there's fewer molecules, so therefore less pressure. So in this case, there's 4 moles over here, there's 2 moles here. So actually increasing the pressure is going to shift it to where there's less molecules. So I'm going to shift it over to the right. So fewer molecules of gas, so therefore shift to the right. And therefore the opposite would be the case if I decrease the pressure. So you need to be careful in counting up the moles, because that's going to help you work out in which direction the equilibrium will shift. Okay, so if I decrease the pressure, the equilibrium will try to counteract it. And as a result, it will try to increase the pressure. So therefore, it's going to go where there are more molecules of gas, which in this case would be the left-hand side. Okay, so it's where there are more molecules of gas, and therefore would shift it to the left. Okay, so it goes to the left of the reaction because there's more molecules of gas and more moles there compared to there. So that's why it would shift it. So it's all about balanced equations, okay, which are gases. Because that allows you to work out where the more moles of a substance will be. Is it the reactant side? Is it the product side? And then as such, you can then say, well, actually, there's 4 moles here. So if I increase the pressure, the system will try to decrease the pressure. So it's going to shift it to where there's less moles. So over here, there's less moles. So therefore, increasing the pressure would favour the right reaction. If, however, I decrease the pressure, it's going to try to counteract to go to where there is more pressure. So therefore, it's going to go where there's more molecules. So as you can see over here, there's 4 moles over here. So it will shift the equilibrium to the left. So just be mindful, that is essentially what it's all about. So if I give you another example of a reaction, you can then try to work out increasing and decreasing and what it would affect. So let's imagine I've got 2 moles of carbon monoxide gas reacting with 1 mole of oxygen gas, and it's a reversible reaction. It's going to produce 2 moles of carbon dioxide. If I increase the pressure, what's going to happen? If I decrease the pressure, what's going to happen? So just pause the video and work that out. So hopefully you've been able to see that on the reactant side, you have got 3 moles of carbon, 2 moles of carbon dioxide plus 1 mole of oxygen. And over here, you've got 2 moles of carbon dioxide. So if I increase the pressure, it is going to shift it to the right because there are less moles on the right-hand side, so the pressure would be less. And as you know, it's trying to counteract. So if I increase the pressure to counteract that, it's going to go to where there's less pressure, which would be over here because there's less amount of molecules. The opposite would be true if I decrease the pressure because there's 2 moles over here, 3 moles here. So it's therefore going to try to counteract that and move to where there is a greater pressure, which would be here because I have more moles on the reactant side. So if I decrease the pressure, that would shift the reaction to the left-hand side. So it doesn't matter what they give you, you've just got to look at, well, how many moles of reactant do I have? How many moles of product do I have? And then you can work out what increasing and decreasing the pressure would do to that reaction. So the last thing I'm going to look at today is concentration, which is probably the most easiest and straightforward one. So when we're talking about concentration, we're talking about the reactants and the products in this case. So if I change the concentration of reactants at equilibrium or the concentrations of products at equilibrium, then the system is no longer going to be at equilibrium. Because if you remember, equilibrium is where the rate of the forward and the backward reaction is the same. So if I change the concentration of either of those, I am changing the system. And as such, I will shift the equilibrium one way or the other, depending on what I've changed. So as you know, the Chatiers principle is that if you make a change to the system tries to counteract that change. So let's look at what increasing and decreasing the concentration would do in this scenario. So let's just write down the following. So if we change the concentration of either the reactants or the products, then we are no longer going to be at equilibrium. Okay, and we know that from the first page when we looked at the graph. So the system will try to change that, try to counteract that by bringing the system back to equilibrium, because that's what Le Chatelier's principle is all about. So the system will try to counteract. So it will respond to bring it back, the reaction back to equilibrium, to bring the reaction back to equilibrium. So let's look at what we mean by that. So if I increase the concentration of reactants, okay, so here I've got nitrogen plus hydrogen. If I increase the concentration of those reactants, then the system will try to decrease this by making more product. Okay, so the system it tries to counteract that. In other words, it tries to bring the concentration of reactants down. And as such, that means you'll make more product. And the equilibrium would shift to the right. Okay, so the concentration of these go up. To counteract that, you're going to shift it to the right because you're going to therefore make more product to bring that down back to equilibrium. Okay, and the opposite is true if I decrease the concentration. So let's imagine in this case I'm decreasing the concentration of product. The system, of reactants. So if I make the concentration of these reactants less, then the system will try to counteract that by making more of the reactants. Okay, so the system tries to counteract that by reducing the amount of product. So if I make this amount less, the system tries to make more of this, so therefore it will shift towards the left of the reaction. So hopefully that's helped you understand a little bit more about the concept of reversible reactions and dynamic equilibrium. Again, if you're still not sure or anything, or if it wasn't clear enough, please just email me. I'm happy to go through it with you, or highlight it to me when I see you in lessons. All right, guys, thank you very much.